Morning, everyone. As you heard, my name is Itumeleng Monageng, and I'm based here at the University of Cape Town, jointly with the South African Astronomical Observatory. So my talk will be about stars. So we just heard about galaxies, but now talking about the other side of research that's happening here. So firstly, I just want to thank the organizers, Patricia and Ross, for organizing this. It's been great. Yesterday was great catching up with everyone and seeing where everyone is. So that's been great. So my NASSP journey started in 2011, and I found some pictures from that year with my classmates. Yeah, I think most of these are from the summer school, and I think I speak on behalf of everyone when I say those 2 weeks were some of the best 2 weeks of our whole NASSP experience. And yeah, so it was great to meet new people from different places, you know, people from all across Africa, from Egypt, Sudan, everywhere, different cultures, different religious perspectives, but we all somehow clicked and connected. We formed friendships during those 2 weeks, and some of the friendships are still in existence. So that was a great experience, and I hope the summer school program or the summer school is still happening as part of NASSP, because that's very important. So just a brief timeline of my postgraduate career. So as I said, I joined the NASSP program in 2011. That's when I started with the honors program. So that's a picture from our graduation. I guess this isn't working. Over there with Kine and others that are not here. And then I went on to the master's program. So I stayed in NASSP for the 6 months of the coursework. And then I did a mini dissertation under the supervision of Vanessa McBride. That's a picture there from that graduation with Sarah, the now HOD. And then, yeah, I continued working on a research project with Vanessa McBride, co-supervised by Marcus Butcher at Northwest and Jazreen Mohammed. Yeah, so that was great. And then after that, I became part of the SOL team, where I was involved with the science operations, so doing service observing for SOLT users. And I did a postdoc briefly at SAO until I took up my position as a lecturer here. So we just heard a lot about galaxies from Michelle. I'm one of the NASSPs that stayed in academia, and I ended up studying stars. I'm particularly interested in interacting binary stars. And in particular, I'm interested in X-ray binary stars. This is a slide I like to use to, I think that nicely illustrates what's happening with X-ray binary. So basically, X-ray binary stars are pairs of stars that are interacting with each other, where one of the stars is a normal star, like the sun. By normal, I just mean that there's nuclear fusion taking place in the center of the star. And its companion is basically the remnant of a dead star, so the end product of stellar evolution. So these are the so-called compact objects. So this can either be a white dwarf, a black hole, or a neutron star. And what happens here is that you have mass transfer happening from the donor star or from the normal star, which is accreted by the compact object, resulting in the X-ray activity, which is why we call them X-ray binaries, because they give off a lot of their emission in the X-rays. So this slide here illustrates the different ways in which this mass can be transferred. So you have here what we call Roche-Lobe overflow, which is basically when you have the star filling this volume of space within which the matter is gravitationally bound. And when this happens, the matter funnels through what we call the inner Lagrangian point, or the L1 point, where because it has angular momentum, it forms an accretion disk around the compact object, and then the matter is accreted. Sometimes the matter is ejected, where we see jets. Another way of transferring mass is through what we call wind accretion. So in this case, you have a supergiant star. The donor star is a supergiant star, which releases lots of gas radially. And then the compact object, as it's orbiting around it, can accrete the matter and release the X-ray emission. But we can have a combination of those two, where we have wind Roche-Lobe overflow, where the star itself doesn't fill the Roche-Lobe, but the slow-moving wind from the star can fill the Roche-Lobe, and then matter can be accreted by the compact object. But in certain cases, we have what we call disk accretion, where the donor star has a disk where the neutron star or the black hole can accrete matter from the disk as it's orbiting around that. Okay, so those are the different ways in which the mass can be transferred, or the interaction happens generally in X-ray binary stars. So as I said, I'm interested in stars, and I think these are the coolest astronomical objects to study. That's just my biased view, but I think they also contribute in the bigger picture. This is a list of reasons why I think X-ray binaries are important in the bigger picture as well. So as I said, there's interaction with the compact object, so they provide the most efficient ways of identifying these end products of stellar evolution, so these white dwarfs, neutron stars, and black holes. Since they are also precursors of gravitational waves and gamma ray bursts, it's important to understand them so that we can understand how these extreme and exotic objects behave. And as I said, there are different types of binary stars, so they're important also for understanding binary evolution and stellar evolution in general, because we see different types of them under different environments. So it's important to study them to understand that. And also in galaxy formation and evolution, because they give off a large, when you look at galaxies, a large portion of the high energy emission comes from X-ray binaries. So it's important to study them even for galaxy evolution. And also for understanding extreme physical processes that we can't otherwise reproduce here on Earth. So they provide ideal laboratories in space for understanding those processes. So I'm particularly interested in, this is supposed to be a movie, I hope it works. Okay, maybe not. Okay, so this is a subclass of X-ray binaries that I am particularly interested in. I study high mass X-ray binaries. So high mass meaning that the donor star is a high mass star. It's an early type star. It's a star that has a mass that's at least 8 times the mass of the sun or so. And in that subclass, or in that class, there's a subclass called BE X-ray binaries, which consist of a BE star. So a BE star is an early type star. It's rapidly rotating, and because of this, there's a disk that gets formed around the equatorial regions, which is variable, and this is the source of the matter that's being accreted by the neutron stars it's orbiting around it. Okay, so the neutron star in these objects generally have an eccentric orbit because of the large supernova kick they gave Earth to this. So we see an eccentric orbit of the neutron star. So when the disk is large enough at close passage, it can accrete the matter. So that's a snapshot of that movie showing where the emission is coming from in these systems. When we look at the BE star and the disk in general, this is where all the optical and the infrared emission comes from. So we use telescopes like Meerlicht and Ogle to look at the photometric, optical photometric behavior in these systems. And also we use spectra, so we use SALT a lot for our research to look at the H-alpha line, for example, because this is a tracer of what's happening around the circumstellar disk. And then the environment around the neutron star gives us a tracer of what's happening in the X-rays, so in the high energy region of the spectrum. So generally, the research that we try to do in this area is trying to answer these questions about how the BE disk and the neutron star interaction happens. So by looking at spectra from SALT and data from X-ray emissions, we try to understand that BE disk and neutron star connection. And also studying BE disk structural changes, which is one of the main areas of research in this area. And more recently, we've seen radio emission, which can give us something, information about the jet formation in these systems with access now to more sensitive telescopes, radio telescopes like MeerKAT. We are beginning to see strong radio emission from these systems. So one of the early projects that I got to work on during my master's, so after leaving NASSP with Vanessa, was this project here where we looked at a sample of BX-ray binaries in the galaxy using SALT amongst the telescopes that we used to basically take the observations and try to get a physical, or try to use some equations to calculate the physical size of the disk and how that varies, and then how that affects the accretion process that happens. So this is an example of a plot from that paper where we looked at one source here, and you can see that, so that's a radius There's radius here in the top plot as a function of time. So you can see how the radius of the disk changes as a function of time. And then here at the bottom, we see the X-ray emission, how that affects it. And we generally concluded that there are two types of outbursts, X-ray outbursts in these systems. And for one of them, we generally see the outburst happening when the neutron star goes by a closed passage, or what we call periastron passage. But for the other type of outburst, the giant outburst, we see it having no correlation or anti-correlation. It seemed random the way these outbursts happened according to the disk size. But then this, we came to find out that this behavior is more complex than how we thought about it. So there could be complicated geometries. For example, if you have the disk plane and the neutron star plane being highly misaligned, then this can cause the disk to be highly eccentric, and then the neutron star can accrete matter from that eccentric disk, resulting in the giant outburst. So this is work that was done by an American group. These are snapshots from the simulations, SPH simulations. You can see that initially the BE disk, so that's the BE star here, and then that's the BE disk and the neutron star. Initially it was circular, but then after a while it becomes eccentric, where the neutron star then can accrete a large amount of matter from the elongated side of the disk, resulting in the giant outburst. So a lot of my work nowadays revolves around trying to understand this, so trying to get observational signatures of this using telescopes like SALT, and also using semi-analytical models to do that. So I work with students to try to do that, because so far this has only been done theoretically using SPH simulations. So another set of objects that I'm interested in are the so-called gamma ray binaries. They're called gamma ray binaries because they give off a large amount of emission in the gamma ray part of the spectrum, but they're also multi-wavelength emitters. And in these systems, we don't quite know what the compact object is. So it can either be a black hole or a neutron star. And because of this uncertainty in the nature of the compact object, there are two main models that try to explain the physics that's happening there. One is the microquasar model, or the accretion model, where there's accretion happening, there's an accretion disk, and then some of the matter is ejected via relativistic jets. And there's particle acceleration happening, so there are physical processes like synchrotron radiation, inverse Compton scattering, and so on, that give rise to the multi-wavelength emission. An alternative to this is if you have a young pulsar that's rapidly rotating and it prevents matter from being accreted, you can have relativistic wind from the pulsar interacting with the slow-moving wind from the massive star, forming a shock region between these two regions, between these two stars, where particle acceleration in that case can take place in between the two stars. And then that is the origin of the multi-wavelength emission. So some of the main questions that we try to answer in this area is what is the nature of the compact object, because that's important to try to distinguish which models at play here. And also, what is the origin of this multi-wavelength emission? So what processes are happening actually, and where are they happening? So I'm fortunate to work with some good students. One of them is Andres Matiba, who's sitting here. So he's also from NASSP. So he's working on a project with me on gamma ray binaries, where he's looking at meerkat data of a sample of objects together with high energy data, X-ray and gamma ray data. And he's trying to use cross-correlation techniques to try to see if there are lags between the emission at these two wavelengths. So he's using simultaneous data or contemporaneous data to try to see if there are any time lags, to quantify any delays for this, and then to see which populations, or to see if the populations of particles, is it the same populations of particles that give rise to this, the different emission. So I recently also got to work on low mass X-ray binaries through my involvement with Thundercat. So Thundercat was a program that was led by Patrick Boat and Rob Fender at Oxford, which looks at different types of transients. I think Miriam spoke briefly about this yesterday. Different classes of transients, including X-ray binaries, gamma ray bursts, cataclysmic variables, and other types of transients. And one of the main questions that that Thundercat was trying to answer was, how does the disk-jet connection happen in low mass X-ray binaries? So basically, how does the accretion and ejection process happen. So the ejection or the radio data from YECAT gives us a gauge of what's happening with the matter that's ejected, so the matter in the extended regions, whereas the X-ray emission tells us something about the more compact regions. So we use this radio and X-ray plane with a bunch of objects here, so we get simultaneous data in the X-rays and the radio, and then place them on here to try to understand how this happens. And what my involvement here has led to publication of a paper on a black hole system that was recently discovered. And also as part of my involvement with Thundercat, I co-supervise a student who's also from a NASSP, Kelebogile. She's doing a PhD with me and Rob and Patrick. And she's also looking at a sample of low mass X-ray binaries, but she's looking at neutron star systems specifically to see if there are any systematic differences between black hole systems and neutron star systems in this disk jet connection. So I do a lot of teaching as well. In my lecturer position, I have to lecture, I guess. Yeah, I teach undergraduate students the third year stellar astrophysics course. And this is a picture of, see some of them are here, of the third years using the teaching telescopes here. So this is one of the optical telescopes up on the roof of R.W. James. And then this is the students operating the 2 radio dishes that are located in SAO, so they can operate them remotely from here. So I'm still involved in NASSP. I do guest lectures for the NASSP MSc Compact Binaries course, where I teach the component on basically my research. And I'm still involved with the winter school, with the teaching of that, and also the organizational aspects of it, which has been fun. And I supervise honors projects as well. So I'm still over here in NASSP. Lastly, I just want to express my personal gratitude to everybody that's been involved in basically my journey to get me to where I am today, from the people that conceptualized this program, Patricia and Peter, and the lecturers and the supervisors. This truly has been a journey among the stars. Thank you.